All right, welcome to part 3 of our discussion on concavity. We've talked about so far graphs and how concavity looks on a graph. We've talked about algebraically, how do you find intervals of concavity, and algebraically, how do you find points of inflection. And these next 2 pages are going to be on the consequences of concavity, basically what happens because we know about concavity. Well, one of the things we can talk about is locations of tangent lines. So using the graph shown, draw tangent lines at each of the 4 points and tell me when do you think the tangent line is above the graph and when do you think it's below the graph. So what I want you to look at is graph your tangent lines and then we'll do a little magic and it will appear. So take a second, press pause, draw tangent lines, make an assumption, make a hypothesis, and then come back. Okay, so hopefully you did that. And when you look at your tangent lines here, hopefully your tangent lines look something like that. Probably not as straight, but something like that. And you can see that 2 of the tangent lines are above the graph and 2 of the tangent lines are below the graph. Now I know you might be thinking this one's kind of to the left of the graph, but it's technically all the lines on this thick black tangent line are above all of the points on this thin graph of f. So what's the difference between these 2 points versus those 2 points? Well, we're talking about concavity, so hint, hint, it's got something to do with concavity. The tangent line is above the graph when the graph was concave down, and the tangent line is below the graph when the graph is concave up. Now, why does it happen that way? Well, one of the other things you can talk about when discussing concavity is you can discuss the slope of f. So the slope of f right here is negative, 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 getting closer to 0. So the slope is negative and getting closer to 0. On this section, the slope of f is increasing. Because it's negative and going to 0, that would be increasing. Here's the slope 0, and now the slope is getting more positive. Here, the slope is still increasing. But right here, the slope is constant. And right here, the slope is constant. So on my tangent line, it's a line. It has a constant slope. So if I attach a constant slope to a slope that's increasing, the constant slope is going to be below the graph. When we're concave down, the slope is decreasing because the slope is positive, 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 less positive, less positive, 0, negative, negative, negative. So all over here, the slope of f is decreasing. My tangent lines have a constant slope versus a decreasing slope. The constant slope is going to be above. All right, and then let's see, moving on here. Describing graphs. We're going to use the same graph and sketch both f and f double prime and then complete the following sentences. So I want you to do this on your own again. I know you're watching a video here, but I want you to try it on your own before I get involved. So take a second, try this on your own, and then magically it will appear. All right, so here goes. We should have drawn in f prime and f double prime, and they should look something like this. So when I drew in f prime, I found the horizontal tangents on f and made those zeros of f prime, and then said f increased, then decreased, then increased. So f prime was above, then below, then above the x-axis. F double prime is graphed based on f prime, so when f prime had a horizontal tangent, f double prime had a 0, and f prime went from decreasing to increasing, so f double prime went from negative to positive. All right, so there's that. Now these fill in the blanks, we need to be very careful and answer what's being asked. When f double prime is above the x-axis, what is f prime doing? Well, when f double prime was above the x-axis, that was from about, I don't know, 0.75 on, and from 0.75 on, f prime was increasing. Now the next question asks, what about when f double prime is above the x-axis? What's happening to f? Well, when f double prime is above the x-axis, f is concave up. So f double prime indicates things about f prime and about f. When f prime and f double prime are on the same side of the x-axis, then the graph of f is getting steeper. So when f double prime is positive and f prime is positive, that would be from here over. And from here over, the graph is getting steeper. When they're both negative, that would be from like here to here. They're both negative. So on the graph of f, that would be from here to here. It is decreasing and getting steeper. On the interval from -1 to -0.1, f is increasing at a decreasing rate because between here and here it's going up, but it's shallowing out. So it is increasing, but at a decreasing rate. And then the next one I think says from 0.6 or 0.7, which is about here, to 1.5, f is decreasing at a decreasing rate. And what I want you to pick up on here is increasing at a decreasing rate was concave down, decreasing at a decreasing rate was concave up. So when these guys don't match, you're concave down. When these guys match, you're concave up. Meaning, if it was increasing at an increasing rate, it would still be concave up. And if it were decreasing at an increasing rate, it would still be concave down. And then last but not least, what did I ask? When f prime has a relative extremum. Okay, now this is a pretty unique one. When f prime has a relative extremum, that's right here, and that goes with this x value. So when f prime has a relative extremum, f double prime has a 0. But we're going to continue that to say, well, wait, when f double prime has a 0 and it crosses through the axis, f would have a point of inflection. So whenever f prime has a relative extremum, not just any horizontal tangent, but when f prime has a relative extremum, f will absolutely have a point of inflection. All right, onwards. The last but one of the most important things about the second derivative is that we have the second derivative test. So you know how we did all that stuff where we had intervals of increase and decrease, and we used those to determine if something was a relative max or a relative min? Well, there's an easy way to do that. If I look at this point right here, this is, I will say obviously, a relative max. Agreed? Of course we agree, Mrs. Fibber. Fantastic. This is a relative max. Well, it's a relative max because f prime of x equals 0 or does not exist, and it bends downward. Wait, bends downward. What does that mean? Oh, yeah. That means that f is concave down, or that f double prime is negative. Down here, this is most obviously a relative min because f prime equals 0, but f bends up, which means f double prime is positive. Hence, the second derivative test is born. If you want to calculate or classify, pardon me, relative extrema, the first thing you need to figure out is, all right, find the potential relative extrema. Find where the first derivative equals 0. Now, the first derivative can also lead to relative extrema where the derivative doesn't exist, but those cannot go into the second derivative test, okay? So any values where f prime equals 0 can get plugged into this second derivative test thing. Let's call those values a. Calculate f double prime of a for those values. If f double prime of a is greater than 0, that means you're concave up and you have a min. Now that might seem counterintuitive. Concave up, min, I don't understand. Well, remember, concave up looks like this. Your minimum value would be at the bottom. And then if you're concave down, you have a max. And then if the second derivative equals 0, the test is inconclusive. You may have a relative max, you may have a relative min, you may have neither. What you need to do then is you would have to go back to the first derivative test, which means test those intervals to determine if you have a relative max or min. All right, so let's see it in action. Determine the intervals of increase and decrease and the intervals of concavity for this, and then state the coordinates of any local extrema or points of inflection. You know what I want to do? I'm going to skip over this. I'm going to jump to example 2, and I'll have you finish with that example 1. I think that makes more sense for time. So let's look down here at example 2. It's known that f of 4 equals 9. Okay, here 4, 9. And it's known that f prime of 4 equals 0, which means right here the graph is flattish. And it's known that f double prime of 4 is 16. Well, I don't care so much about the fact that it's 16, but I do care that that's positive. So that means this bends upward. Is 4, 9 a relative max, relative min, or neither? It's a relative min. And we figured that out by the second derivative test, which is a perfectly legitimate justification, by the way, if you're ever asked to classify a critical value. All right, number 3, use the second derivative test to classify all relative extrema. So here's how the second derivative test works. We want to take the derivative to find the critical points. So we're going to take g prime, which is going to be negative 4x cubed plus 12x squared minus 8x. and I'm going to set it equal to 0 or find where it doesn't exist. Well, this is a polynomial. It always exists, so that's not going to happen. Let's find out when it equals 0. So I'm going to pull out a negative 4x. I'm going to be left with x squared minus 3x plus 2. And I'm going to factor minus 2 minus 1. X equals 0, 2, and 1. These are all critical points. Now, if we were going to do this the long way and classify the relative extrema, I would have to go from negative infinity to 0, 0 to 1, 1 to 2, 2 to infinity, test them all, figure out when it up, there's a lot to do. The second derivative test bypasses that and says, you know what? Don't make intervals. Just take your critical points and then come over here and find g double prime, negative 12x squared plus 24x minus 8. And then find g double prime of 0, g double prime of 2, and g double prime of 1. In other words, evaluate the second derivative at the critical points. All right, g double prime is 0. 0, 0 minus 8. G double prime of 0 is negative 8. G double prime of 2. Negative 12 times 4, negative 48 plus 48 minus 8. So negative 8 again. G double prime of 1, negative 12 plus 24 minus 8, that's going to be a positive what? Positive 4? I think it's positive 4. Okay, so there's the values of the second derivative. This tells me that g is concave down at 0, which means that 0, comma something, is a relative max, because concave down looks like a frown, has a maximum on top. It also tells me that g is concave down, there we go, concave down at 2. Therefore, 2 comma whatever is another relative max. And last but not least, g is concave up at 1 because g double prime of 1 was positive. Therefore, 1 comma whatever the y value is a relative min. Okay? And I'm done. That's it. That's the second derivative test. I've identified the x values of the relative extrema without having to do intervals. Easy peasy. Tons of fun. All right, how am I doing on time? It's 12 minutes. So here's what I want you to do. I want you guys to go back, try part A, get through all your intervals to make sure you know how to do it, and then come back and briefly look at it, and then we'll stop this. See you in a second. Press pause, do part A, press pause now. All right, you're back. Let's go through this quickly. So, we were supposed to find intervals of increase and decrease and intervals of concavity. To do both of those things, I would need to know the derivative and its zeros, and the second derivative and its zeros. To find the intervals of increase and decrease, I made intervals using those as endpoints. To find intervals of concavity, I used 5/3 as an endpoint. And voila, those are the intervals. And then to find coordinates of any local extrema, I came over here and I said it went up and then it went down, making 2/3 a max. It went down and then went up. 4 is a min. And I didn't have a calculator on me, so I just left it as negative 2/3. F of 2/3 are the coordinates of the local max, and 4f of 4 is the coordinate of the local min. And then the points of inflection, it went from concave down to concave up, would be right here. And one thing I want you to notice is that at negative 2/3, that would be in this interval, f is concave down, making it a max. And at 4, which is on this interval, f is concave up, making it a min. That is all, ladies and gentlemen. So you are done with concavity. Now we just got to use it. Toodles.